and what are the conditions for minimum. That is, at any point of the screen, we will get maximum or minimum. That will depend on which wave is superimposed, which superimposition you are considering. What is the angle theta? So today we are mainly going to discuss where will be the position, that is angular position, linear position, as well as angular width and linear width. And then we will see the graph, intensity versus phase difference graph, or the position on the screen that graph will plot. So what was the arrangement? Suppose first we'll understand what is the meaning of this arrangement. Suppose this here was the source. In case of Fraunhofer diffraction, we require, condition was the source and screen both must be at infinity. But practically, how is it done? So just this slit, main slit is this one. This is not the diffracting slit. From this slit, the rays are coming the diverging one. Okay, maybe like this, the rays are coming. Now, when it is passed through a lens, maybe a convex lens, so the rays will become parallel. When this will happen? When the distance between this slit and the lens is equal to its focal length, whatever the focal length of this lens is. Now, these rays are allowed to pass on the diffracting slit. So, when these rays are allowed to pass through this diffracting slit, now we can consider many more. Now, after this, different possibilities are there. Here also, as we are considering plane wave front, so screen should be at infinity. But practically, what is done? Practically, here we are taking again a lens. Very close to the slit. And the screen is placed at the focal plane of this lens. So these rays which are coming directly like this, they will converge at the center. So this is central maximum. The rays diverging at any angle may be this way. They may converge at any point here. The rays which are propagating in this direction, this way, they may come somewhere else, may meet somewhere here. So this distance is approximately d. Actually, this is up to only focal length. And the lens is placed very close to the slit. So this distance is approximately capital D, which is distance between this diffracting slit and the screen. So this is the experimental arrangement. This we call central fringe. At P1, we may get bright or dark depending on what? This angle theta. Suppose this is the main ray, this angle is theta. So depending on this angle, at P1 we may get dark or bright. Similarly here also. At P2 we may get dark or bright depending on that angle theta. and we have got the condition. What was, we have placed the length here, so the ray which is going far and deviated like this will be theta. Similarly, this side also, maybe like this. This is P2, suppose. This may be theta dash. So we have got the condition for, or at P we may get dark under what condition? At P intensity is minimum if A sin theta is L lambda. Or this theta is sin inverse L lambda over A, which is approximately L lambda over A if this is very small. Generally, this lambda is of the order of 10 to the minus 7. If this is coming of the order of minus 4, then also it will come nearly 10 to the minus 3. So that in that case, theta will be very small. If you are not getting small one, especially while solving the numerical, you have to see what is the value of this one. Sin theta equal to L lambda by A, how much we are getting? 0.5, 0.6, if like this you are getting, then we will find 0 sin inverse. If you are getting sin theta equal to 0.006 like that, then same thing in radian only we will say. Or as your calculator is allowed for you, so you can find the value. So always prefer this one then. Okay. And at P intensity is maximum, this we call secondary maximum because this is the central one. Center is at O. If A sin theta is 2n plus 1 lambda by 2. So these are the conditions which we have derived. Now today we will see the angular position and angular width of different maximum. What will be the angular position? What will be the angular width? What will be the linear width? That part we will discuss today. Yes, shall we rub?
Yes, sir.
What?
Yes, sir.
Now, angular position and linear position. Angular position, linear position, and width also. Okay. Angular and linear. And width. Mainly it is a central maximum. So how will you find? So we are making Just to understand, we are making one figure here again. Suppose this is the screen. This D, which is approximately equal to the focal length of the second lens. If sometimes it is given lens, then in that case, because lens is placed somewhere here only. So this is our central maximum. This is suppose first dark, and this is suppose here first dark this side. So this angle will be the θ1 will give this we call semi-angular width of central maximum, because from here to here we are getting light, but intensity is maximum here. At this point we are getting dark. Again light is coming. So just I am making big only. Suppose this is the bright one, first bright. Here again we are getting first bright. This is second dark. So we are going to measure the different angles. So what is the angular position of first dark? Of first dark. This θ1 will be sine inverse lambda by A. But for first dark, A sin theta is lambda by A sin theta is lambda for first dark. So this is both sides. Now, from here to here we are getting central maximum. From here till here, we call it central maximum. So if you are asked what is the angular width of central maxima, so indirectly what you have to find? θ1. And how much it will come? θ1 is this one. So this is this side also and this side also. So from here to here, this is the angular width of central maximum. Because central maximum is from here to here. Dark, first dark is coming here and first dark this side is coming here. So theoretically, the width of the central should be this much only, but due to diffraction we are getting width more than the width of the slit. Width of the slit is only A, but here if we find linear width, it will be more than A. So this is 2 θ1, that is 2 sine inverse lambda by A. It will be approximately 2 lambda by A if A is much more than lambda. That is, if lambda by A is coming very small, condition is same for theta, very small. So this is angular width. If you are asked semi-angular width of central maximum, that is θ1 only. semi-angular width. So angular position of dark or semi-angular width of central maximum, same. Angular width means from here to here, this angle. Semi means half, so only this part. So that is theta 1. So that is semi-angular width. So sine inverse lambda over 8. Now, angular position of first secondary maximum, what will be? First secondary maximum, that is this one. So we have to find from here to here. Theta 1 dash we have said. Theta 1 we are writing for dark, and suppose for bright we are taking dash. What will be the condition? For at point P we will get maximum under what condition? A sin theta is 2n plus 1 lambda by 2. That is, this theta 1 dash will be how much? 3 by 2. Sin inverse 3 lambda by 2a. So here it will be A sin theta will be 3 by 2 lambda. For bright here, condition is the path difference between the two extreme rays of the same wavefront. Here it is not the two rays of two different slits. Two extreme rays of same wavefront must be odd multiple of lambda by 2. And we will start from third one, 3 lambda by 2, 1.5, because lambda by 2 is coming somewhere here only, within the central maximum only. So that's why we are not considering that first secondary maximum. First secondary maximum means after dark. So that's why we are taking that one, 3 lambda by 2a. Okay. Now, angular position of second dark. That also you have to find. Angular position of second dark. What will be? That is theta 2. Sine inverse 2 lambda by 8. That is from here to here we are taking theta 2. Now, if you are asked what is the angular width of first secondary maximum, angular width of first secondary maximum. What will be? From where to where? First secondary maximum is from here to here. That is this angle minus this angle. So this one will become theta 2 minus theta 1. So we'll find theta 2 from here, you will find theta 2 from theta 1 from here, and we'll subtract. You will find in degree, you will find in radian. So this is the angular width of first secondary maximum. So this is angular position and angular width. It may be both sides. This side also it may be. Sometimes it is asked, what is the angular width of first dark on both sides? Meaning is same. Angular width of central maximum. First dark here, first dark here. Angular width of this, that is angular width of central maximum. Angular position of second dark on both sides. Indirectly you are asked to find theta twice of theta 2. This is theta 2 this side, similarly theta 2 this side. So twice theta 2 you have to find. This is angular. Now we'll see linear. Linear width means from here to here this distance. Suppose this is y1 from O to D1, and O to D1 dash is also y1. Okay. So linear width of central maximum, that is D1 to D2, this distance, twice y1 you have to find. So first we'll find what is the semi-linear width. Semi-linear width, or the distance of first dark from central maximum. Distance of first dark from central maximum. This is y1. And how will you find y1? So this tan theta 1 is y1 over d. y1 is d tan theta 1. As you know, this d, which is the distance between slit and the screen, is approximately equal to focal length. So sometime in place of d, you will be given focal length of the lens. So it is approximately f tan theta 1. Since this d is approximately equal to f. Now, if angle theta 1 is very large, or then we will find this one tan theta 1. Sin theta 1 we have got. So tan theta 1 we will find from there. Otherwise, if theta is small, then this y1 will be y1, which is equal to d tan theta 1, is approximately d sin theta 1, and sin theta 1 we are knowing. What is that? Lambda over 8, or approximately f lambda over 8. This is our semi-linear width. Now linear width of central maximum. This is 2y1. Naturally, twice of this. So this is 2d tan theta 1, approximately 2d sin theta 1, approximately d 2d lambda by 8, or it is approximately twice f lambda over 8. Now, similarly, when we ask what is the distance between first secondary maximum and central, then what you have to find? Distance between first secondary maximum. Or distance of first secondary maximum from central bright. So here what is happening, from here to here again we are getting light, but at this point we are getting maximum light. Dark will be only at particular point, but bright will be in a range, and where in that range here intensity is maximum. That's why we say here is the maximum. So from here to here again we are getting light. So what indirectly what we have to find? We have to find from here to here. This is the bright. So this y2 we have to find. So this is equal to y2. And how will you find y2? So this tan theta 1 dash is y2 over d. Again, same way, if this one is theta is small, we can take sin theta 1, otherwise we have to find this value. So this way we can find linear position or angular position, angular width or linear width. Suppose here you are asked, what is the linear width of first secondary maximum? That means from where to where you have to find? So from this to this length you have to find. That is, we will find, suppose this is y3, this is y1, then y3 minus y1 you will find. So whatever it is asked, accordingly we can find. Generally it is asked central width, angular width of central maximum or linear width of central maximum, position of first dark, angular position of first dark or linear position of first dark. Sometimes first secondary maximum is also asked. So this way you have to solve the numerical. So variation of intensity. In case of interference, the maximum, all the maximum were having same intensity. But here this is not the case. In this case, intensity of the central maximum will be very high in comparison to that first bright, much low, then second very low. So here there will be variation of intensity, okay, versus angular position. This theta is here, angular position. Angular position. So from this graph it is very clear. See, this is the central maximum. So intensity of central maximum is very high in comparison to these two. This is first secondary maximum. This is second secondary maximum. So intensity keep on decreasing. In case of diffraction, we are not getting more than 3 fringes both sides. Whereas in case of interference, we are getting many fringes. We can't count. So many fringes we are getting. But in case of diffraction pattern, generally we get 2-3 fringes on both sides. And the intensity varies. So this is our central maximum that is at 0, theta equal to 0. What was here is first dark. So what was the condition for first dark? What was the angular width? So this is sine inverse lambda by A, or simply lambda by A you can write, provided theta is very small. This is second dark. So this is first dark, D1 this side, this is D2. This one was 2 lambda by A. This is third dark, 3 lambda by A. Now this is the position of first secondary maximum. So this intensity is much less. Generally it is 1/5, I think. We are not sure. Maybe whatever the ratio may be. I think 1:5:27, like that it is coming ratio. So we are not interested in that. So what will be here? So this is 3 lambda over 2A. Lambda by 2A is coming somewhere here only. That's why we are not considering this one first secondary maximum. First secondary maximum is here. Similarly, this side also you can do. So this is minus lambda by A. This is minus 2 lambda by A. This is minus 3 lambda by A. This is first dark. This is second dark. This is third dark. This is first secondary maximum. And here it will come minus 3 lambda over 2A. Here it will come minus 5 lambda over 2A. Here also this is second bright. So this is 5 lambda over 2A. So this graph is frequently asked in 2 marks question. Sometimes, yeah, generally 2 marks question only it is asked. Intensity versus angular position graph. Not phase difference. Phase difference will be in case of interference. So here it is angular position. So this is our central maximum. So central maximum is from here to here, both, all. But at this point, intensity is maximum. So this is our first central maximum, this is our first bright, this is second bright. So intensity keep on decreasing. Now another one may be the intensity versus position graph. This is I versus theta graph, where theta is angular position. Second one may be intensity versus position graph. So this Y is position or the distance from the central grid. So this y-axis will remain same, but here this leveling will change. So if it is I versus y graph, this will be 0. What was the position of first dark? It was d lambda over a or f lambda over a, where d is what? Distance between diffracting slit and the screen. This is 2d lambda over a. Similarly, this one will be 3d lambda over a. Here it will become 3d lambda over 2a. At this place it will become 5d lambda over 2a. Similarly, this side minus d lambda over a minus 2d lambda over a minus 3d lambda over a. So this way we can show the variation of intensity in case of diffraction pattern. In case of interference pattern, what was that? All these maximum were same, and that was equal to 4i. If the two slits were of same amplitude or same intensity, then it was 4i. All the maximum were same, but here the intensity of the maximum keep on decreasing. So this is variation of intensity. Now the difference between interference and diffraction and diffraction. What happens in case of interference? In interference, there is superimposition of two waves coming from two different coherent sources. We have tried that part, or it is due to superimposition or superposition of waves coming from or propagating from, you can say, from different part of same wavefront. Whereas here what is happening? It is due to superimposition or superposition of two waves propagating in same direction or simply direction same in both, there also propagating from two different coherent sources. That is two different wavefront. Here, two different points or many points of same wavefront, but here it is two different wavefront. So it is two different wavefront. And those two different wavefront must be having constant phase difference. That was the condition, that is coherent source. But here that is not the case. As they are part of same wavefront, so always they will be in same phase. In this case, many fringes are observed. Here, only a few fringes are observed on both sides. Many fringes are observed on both sides of central fringe. Here, only a few. If it is single slit, then both sides of the central fringe. If it is straight edge, different conditions there. But the number of fringe will be very few. In this case, intensity of all the bright will be same. That is, all the maximum will be same. But here, intensity of maximum are not same. They vary. So intensity of all the maximum, that is bright, are same. Here, intensity is different. Bright or secondary maximum we call. Or not same. So these are the main two differences. Only 2, 3. Sometimes it is asked 2 different. Sometimes 3 difference can be asked. So this way we will write the 3 difference.